ever have that feeling like one tiny decision years ago could have spun your life onto a completely different track?
Oh, definitely. That what if moment.
Exactly. That
Yeah.
almost job, the road not taken. It's the stuff of movies, right? Like Gwyneth Paltrow in Sliding Doors, she misses a train,
Uh,
and suddenly her life just splits. Two completely different realities playing out.
it's a great example. And it taps into something, doesn't it? That intuitive sense of branching paths.
Well, quantum mechanics takes that idea and really runs with it to this mind-bending extreme called the many worlds interpretation.
It really does. It proposes that those what ifs aren't just hypotheticals, they're actual physical realities existing alongside ours.
Right. So, welcome everyone to this deep dive. We're plunging right into the many worlds interpretation, MWI for short, and forget just alternative versions of your life.
Yeah, it's much bigger than that.
The idea is that like countless worlds are constantly splitting off from ours every single time a quantum event happens.
And it might sound like pure sci-fi, but the MWI is, a serious contender in physics, trying to make sense of quantum
You
mechanics.
might have heard of it. It's definitely colorful. It gets talked about a lot.
It does. So our aim today is to unpack it. Look at the core ideas, why it was proposed in the first place, mainly to deal with some tricky quantum problems and weigh the arguments.
And to do that, we've got some great sources lined up. We're looking at Wikipedia's overview of quantum interpretations, the Stanford Encyclopedia of Philosophy's really detailed entry on MWI.
That one's quite thorough.
Yeah, and some articles from the MIT Press Reader and Quantum Magazine that explain it, but also, critique it. So ready to explore this branching reality,
Absolutely. Okay, let's kick things off with the fundamental concept.
the core idea.
Right. So the many worlds interpretation. It was first properly explored mathematically by Hugh Everett back in the 50s, later popularized by Bryce DeWitt. And its main goal, really, is to get rid of the whole mystery around wave function collapse. It just says it doesn't happen. Instead, all possibilities become real.
So every time a quantum measurement, or any quantum event really, has different possible outcomes, all of those outcomes actually happen, each one in its own brand new world.
Exactly. A separate world splits off for each outcome. And importantly, this isn't just happening in physics labs.
Right, you mentioned like a supernova.
Yeah, or just radioactive decay, anything quantum. It's happening everywhere, all the time. The universe is constantly sort of forking.
Wow. And the main reason for suggesting this rather extreme idea was the wave function collapse.
Pretty much.
Yeah.
In the standard picture, you have this wave function describing a system in like multiple states at once, superposition,
Okay.
but then you measure it and bang, it seems to just suddenly pick one state, one outcome. The wave
Yep.
function collapses.
And that collapse feels weird, like it doesn't fit.
It feels like an add-on, yeah.
Yeah.
It doesn't seem to follow smoothly from the main equation of quantum mechanics, the Schrödinger equation, which describes how things evolve deterministically over time.
So, Everett, and you mentioned Schrödinger had similar ideas earlier.
Yes, interestingly, Schrödinger had toyed with related concepts philosophically, but they didn't really gain traction then. Everett focused on the math.
Right. So they thought, what if it just doesn't collapse?
What if the wave function just keeps evolving smoothly, according to the equation, and all those possibilities it describes just continue to exist, but in different branches, different worlds?
And Everett called this splitting?
He introduced that idea, yeah. Yeah. DeWitt later really emphasized it, suggesting these splits happen with every single quantum transition, everywhere, constantly spawning new realities.
It's almost dizzying to think about the sheer number of worlds. Did Everett's original work go beyond just splitting?
Oh, yes. His PhD thesis was really about the universal wave function. He argued that this wave function, describing the entire universe, is the fundamental thing. Everything else, including us, the observers, emerges from it.
So the wave function is reality, in a sense.
That's the idea,
Yeah.
which connects MWI to really deep questions in cosmology, maybe even how to unify quantum mechanics with gravity.
Okay, so we have this picture. Reality is constantly branching, stemming from this universal wave function that never collapses. But, it sounds incredibly complicated. What are the big conceptual problems people run into?
That's a really key point. There are sort of two parts to MWI. First, the math. The universal wave function evolving according to the Schrödinger equation. That's pretty well defined.
Right.
The second part is, How does that mathematical state correspond to what we experience?
Hmm.
Our perceptions, our sense of being in one world. That's where it gets philosophically tricky.
Because we don't have a rigorous definition of our experiences in that framework.
Exactly. And also, our language just wasn't built for this. We talk based on experiencing one world, so describing multiple parallel realities gets awkward, you know?
Yeah, that makes perfect sense. It's like trying to describe color to someone who's only ever seen black and white. The concepts are missing.
Precisely. And it helps to contrast it with other interpretations, like Bohmian mechanics.
Right, that's another way to avoid collapse.
Yes. Bohmian mechanics adds extra bits to the math-specific particle positions, which directly give you a single, definite world that we experience. But,
There's always a but.
yeah, the cost is non-locality. Actions here instantly affecting things way over there, which many find just as weird, or weirder. Different interpretations trade different kinds of weirdness, basically.
Okay, so MWI avoids collapse and non-locality, but gets this massive proliferation of worlds and the experience problem. Now, what about me? If the universe splits, who am I?
Ah, the identity question. It's a big one. In MWI, you at any specific time are defined by the state of your body and brain in that particular world.
So after a split, there are multiple versions of me, each slightly different based on the outcome in their world.
Kind of, but it's more that the you before the split corresponds to all the yous immediately after it in the different branches. Think of it like a branching tree trunk.
Okay, so the me right now is the trunk.
And future quantum events create branches, leading to different future versions.
Which explains why I only remember one past. Because my current self is on one specific branch, tracing back.
Exactly. The you, say 2024, only shares a history with one specific you from 2023. But that 2024 you will correspond to many different yous in 2030, depending on the quantum events between now and then.
So asking which future me will I be doesn't make sense.
With an MWI, no. You correspond to all of them. There isn't a single thread of consciousness that randomly picks one branch to follow.
Wow, that definitely messes with your intuition about selfhood. But okay, if everything happens, what about probability? Why do quantum experiments look probabilistic if every outcome is guaranteed somewhere?
That is probably the central challenge for MWI. If it all happens, where does probability come from?
Yeah.
It seems like the probability of anything should be 100%, right?
Yeah.
So this is where Lev Vaidman introduced the idea of the measure of existence of a world.
Measure of existence. Is that like how big a world is?
No, not physical size. It's more like a world's weight
Yeah.
or its capacity to interfere with other worlds in certain theoretical situations. And crucially, it forms the basis for the illusion of probability.
An illusion. Okay, how does that work?
Think about the sleeping pill experiment. Imagine you take a pill, fall asleep. While you're out, a quantum measurement is done, say, spin up or spin down. If it's spin up, you put in room A, spin down room B. The rooms are identical.
Right.
You wake up, you're in one of the rooms, but you haven't opened your eyes yet. You don't know which one. Can you meaningfully talk about the probability of being in room A?
Well, yeah, from my point of view, it's 50-50, right?
Yeah.
Even though in that specific reality, I am definitely in one or the other. I just don't know which yet.
Exactly. That's the key. Vaidman argues it's similar after a quantum split. All outcomes happen in different worlds, yes. But each version of the observer, immediately after the split, is ignorant of which specific branch they are on.
So the probability comes from my ignorance about which world I landed in.
Right. And the measure of existence associated with each branch, which comes from the square of the wave function's amplitude for that branch, like the standard Born rule, dictates the subjective probability that observers should assign to being on that branch.
So worlds with a higher measure feel more likely from the inside, even though they all exist.
That's the idea. It's not that they are more real, but that the measure governs your rational expectation of which outcome you'll find yourself experiencing.
And this leads to the behavior principle.
Yes. The principle suggests we should care about or bet on successive worlds in proportion to their measure of existence. So MWI believers should rationally behave just like someone who believes in standard probabilistic collapse.
So you wouldn't like play quantum Russian roulette thinking, oh, well, there's a version of me that survives.
That would be irrational because the total measure of existence of the worlds where you don't survive quickly becomes overwhelmingly large. Your future selves across the branches wouldn't thank you for it, so to speak.
That's kind of comforting. But it still feels a bit abstract, this probability from ignorance. Has this explanation satisfied critics?
Not entirely. There's definitely ongoing debate. David Albert, for instance, argued Vaidman's probability emerges too late after the measurement. How can it guide decisions before the measurement.
That's a fair point.
Weidman and others counter that the measure works as a rational betting strategy even for the pre-measurement self, since that self corresponds to all future outcomes. There are also complex attempts to formally derive the Born rule probability from MWI principles, often using arguments about self-location uncertainty as worlds diverge. Well, it's still a hot topic.
Right. Sounds like it. Okay, besides probability, what are the other big objections people raise against MWI? It feels like such a radical departure. There must be more hurdles.
Oh, definitely. One major one is just the sheer extravagance. Roland Omnes called it the proliferation of worlds objection.
Right, the idea that every tiny quantum flicker creates a whole new universe.
Yeah. Does a slightly different arrangement of photons splitting off warrant a whole new cosmos? It seems to give enormous significance to tiny differences. Feels like overkill, violating Occam's razor, perhaps.
It does feel wasteful, almost. What else?
Well, we touched on the problem of selfhood. If I am constantly splitting, what does personal identity even mean? Does it undermine the meaningfulness of, well, me?
Yeah, that lingering question, does I become just a label for a constantly branching process?
Some philosophers argue it does dilute identity. Even proponents like David Wallace acknowledge that our normal understanding of I might require consciousness to somehow stick to a single branch, but it's unclear how or why that would happen within MWI.
Okay, what other problem?
There's a more technical one, raised by Tim Maudlin, sometimes called the wrong type of object argument.
Wrong type of object.
The universal wave function, the fundamental thing in MWI, doesn't exist in our familiar 3D space plus time. It exists in a hugely complex, high-dimensional mathematical space called configuration space.
Okay. So how does our everyday world, our space-time, emerge from that?
That's the question. How does the concrete reality we experience get generated by this abstract mathematical object in configuration space? It's a gap that needs bridging.
Are there proposed solutions?
There are attempts. Some suggest looking at things like particle densities in space-time, derived from the wave function in different worlds. Others, like Wallace and Timpson, propose ideas like space-time state realism to try and build a 3+1 dimensional picture directly. But it's very much an area of active research and debate.
So connecting the math to our lived reality is a major ongoing project for MWI.
Absolutely. And then there's the probability issue again, sometimes framed as an incoherence problem. How can you talk coherently about probability if everything certainly happens? We discussed the illusion explanation, but it remains a sticking point for many.
Right. And didn't John Bell have some thoughts? He was known for his work on quantum foundations.
He did. Bell found MWI intriguing, especially for potentially resolving the EPR paradox, the spooky action at a distance. But ultimately, he famously called it an extravagantly vague hypothesis. High praise and harsh criticism all at once.
Extravagantly vague. Quite the description. Okay, so lots of objections. But despite all that, people still champion it. What's the big draw, apart from ditching wave function collapse?
Well, one really fascinating argument, pushed hard by physicist David Deutsch, comes from quantum computing.
Yes. How does that connect?
Deutsch argues that the only way to understand the incredible power of quantum computers is through the multiverse. He claims they work by effectively performing calculations in vast numbers of parallel universes simultaneously.
So the quantum bits, the qubits, exist in superposition.
Exactly. And each part of that superposition corresponds to a different parallel world. The computation happens across all those worlds at once.
So if you have a quantum computer with, say, 300 qubits, that's 2 to the power of 300 parallel calculations.
Yes, which is an absolutely astronomical number, more states than atoms in the observable universe.
Wow.
Deutsch asks, how could a physical object confined to our universe possibly perform such a massive computation? Where does the processing power come from, if not from tapping into resources in other universes?
That's a pretty compelling argument, especially as quantum computers get better and actually start solving real problems classical computers can't touch.
It is compelling. It offers a potential physical explanation for why quantum computers are powerful, linking this seemingly abstract interpretation to tangible technology. It forces a choice, which is stranger, countless universes, or this almost magical computational power appearing from nowhere, which carries more metaphysical baggage, as John Wheeler might put it.
That really puts it in perspective. Okay, so we've covered a lot of ground here.
We have. It's a complex topic.
So, summing up, the core idea. Universe constantly splitting at quantum events, creating myriad worlds, all to avoid wave function collapse.
That's the gist. driven by a desire for a more mathematically pure quantum theory, perhaps.
But it comes with huge conceptual challenges, probability, identity, the emergence of our world, the sheer number of universes.
And crucially, we have to stress, there's currently no experiment that can tell us if MWI is right and, say, Copenhagen or Bohmian mechanics is wrong, or vice versa.
It's still firmly in the realm of interpretation, despite the quantum computing argument.
Absolutely. It remains a subject of intense research and philosophical debate. Fascinating, but unproven.
It definitely forces you to confront just how weird quantum mechanics is and how much our everyday intuition breaks down at that level.
It certainly does. Which leads us to a final thought, maybe something for listeners to chew on. If the many worlds interpretation is correct, if every possibility really does happen in some world, does that change the meaning of our choices here? Does it make them less significant because all outcomes occur anyway?
Well, does it give a different perspective, maybe a more expansive view of reality's potential?
Exactly. Does the explanatory power, the elegance it might offer to physics, justify adopting what Wheeler called its heavy metaphysical baggage? Or is it, as critics suggest, maybe too extravagant, too vague, pushing us to keep searching for a different, perhaps more coherent picture of quantum reality, something to ponder?